Greetings, I am Michael Jericho Christian Aison, and in this video, we will be discussing about the different types of air navigational aids. First, let us define what air navigation is. Basically, the basic principles of air navigation are similar to the general navigation. These are planning, recording, and controlling the movement of aircraft from one place to another. Basically, air navigation is the same as any other type of navigation, and the only difference is that we are navigating through the air. Here are the different air navigational aids. We have marker beacon, ILS localizer, VOR, and the ILS glide slope. However, these first four, we will not be discussing them because they will be tackled in a separate video. In this video, we will be focusing on the last three, which are the DME, which was introduced in 1946, TACAN, which was introduced in 1950, and the ATC-RBS, which was developed in 1956. First, we have the Distance Measuring Equipment, or the DME. This navigational aid began development in 1946, but it only became practical for commercial use by the 1960s because receiver equipment became much cheaper due to the introduction of solid-state receivers. And the DME was also a modification of World War II era navigation systems such as the LORAN and G, which were discussed in my previous video. And the DME is an attachment to the VOR. As we can see on the figure on the left, the DME looks like it employs the concept of triangulation, and we will be discussing about the concepts of the DME in a short while. Let us have a short review of what a VOR is. VOR stands for Very High Frequency Omnidirectional Range, meaning it is only available for short-range navigation. VORs are only receivable from 25 nautical miles up to 140 nautical miles usable radius, and line of sight meaning that if there is a mountain between you and the VOR, you cannot receive a reliable signal even though you are within its range. Now, omnidirectional comes from the Latin word omni, which means all or every, meaning that the VOR sends out signals or throughout 360 degrees, which can be received by a VOR receiver. VORs work in a similar manner as a lighthouse. A lighthouse has a rotating light inside, flashing a Morse code so the sailor can write it down and determine his whereabouts. Picture a white bright light shining through all directions and a red directional light that is rotating around the white light. Now once the red directional light passes through the magnetic north, the white light goes off for a second and then you start your timer and wait for the red light to pass by and stop the timer again. Now if you know the rotation speed of the red light, let's say 360 degrees for 60 seconds and you've just timed 20 seconds, that would mean 60 seconds equals 360 degrees. 20 seconds are how many degrees? 20 seconds times 360 degrees divided by 60 seconds, that would be equal to 120 degrees. Piece of cake. In an aeronautical chart, this big ring in the middle indicates a VOR, and it comes in different types. This one indicates a VOR only, just like in Southampton in southeast of England. And this one indicates a VOR DME, so a VOR that is integrated with a distance measuring equipment to tell you how far you are away from the VOR, just like this one shown in the screen. The DME tells you how far away you are from itself. It does not perform any triangulation like how it seems to, but it tells you your slant distance away from itself. For instance, in this scenario, the DME tells that you are 5.4 nautical miles away. If you ever know your altitude, which is 2 nautical miles for this example, via Pythagorean theorem, you know that your horizontal distance is 5 nautical miles, or your actual distance. If you are directly above the DME, it's gonna tell you your altitude, which is 2 nautical miles for this example. DME works on the second radar principle. Here, it is sufficient to say that the ground station is fitted with a transponder that responds to interrogation signals sent by an aircraft tuned to the correct frequency. An aircraft sends out an interrogating pulse, and then the ground station transponder responds by retransmitting a strong signal that is received in the aircraft. The DME equipped on board the aircraft records the time interval between the transmission of interrogation signal and the reception of response to calculate the distance. DME transmission obeyed the line of sight rule. Thus, the higher the aircraft than the beacon, the greater the theoretical reception range. Maximum line of sight range is calculated using this formula shown. Intervening high ground means that in order to receive the DME readings, the aircraft must be on a higher altitude. Accordingly, VOR and DME are two completely different things, but the combination of the two makes for a great navigation tool. A VOR is a radio station which the aircraft uses the radio waves to determine the heading it has to fly towards that station. A DME is a different kind of station that tells an aircraft how far away it is from that specific station. As you can imagine, by combining these two navigation tools, a pilot can easily fly towards such a station, which can be located near an airport for instance. Now, let us say we are on the Grand Canyon, and the VOR points to 310 degrees. Then, we say we are on radius 310 from the station or northwest of Grand Canyon VOR. So regardless of your current heading you're flying, you've just determined your position. Then, you grab your VFR chart, draw a line from Grand Canyon VOR at 310, check your DME distance, let's say 25 nautical miles from the Grand Canyon VOR, draw a 25 nautical mile circle, and then you have your location on the map. Here are a few things that we must note about the DME. The DME gives the slant distance between the beacon and the aircraft, so it is a bit off from the actual distance. But the slight error in distance is actually quite negligible. Also, if a DME station is overloaded, that means there are too many aircraft sending interrogation signals to the DME station, it will automatically lower its sensitivity and only respond to the nearest aircrafts. This is because the strongest signals as received by the DME station actually come from the nearest aircrafts. Unfortunately, VOR DMEs are gradually being made obsolete, and they are being replaced by the far more accurate and reliable GPS. Moving on, here we have the tactical air navigation, or the so-called TACAN. It started development in 1950 and is also referred to as the VORTAC, or VOR TACAN. It works similarly with the VOR DME, but is far more accurate and more portable. VOR DME is actually its civil counterpart, with the VORTAC being primarily used for military purposes. The figure on the right shows a VORTAC, and it is portable enough to be carried by a truck. And for that reason, it is more expensive than a VOR DME, and it is too expensive to be used for civil purposes. However, everything else, every concept that it employs, is the same as the VOR DME. Finally, we have the air traffic control radar beacon system. The ATCRBS started development in 1956 and was the first radar system for air traffic control. It was based on the military's IFF, or the identification friend or foe. And it is also an interrogation based system, and it is composed of a 1030 MHz ground-based interrogator and an aircraft-mounted 1090 MHz transponder. An ATCRBS system consists of the following elements. First is a ground-based radar. Now, this ground-based radar has two antennae, the primary antenna and the secondary antenna. Second, it has an aircraft-mounted transponder. And by the term transponder, it means to transmit and to respond. because its only purpose is to respond to the interrogation signals being sent by the ground-based radar. The figure on the left shows a ground-based radar. As we can see, it comprises of two antennae. The one on the bottom is called the primary antenna, and the one on top is called the secondary antenna. The purpose of the primary antenna is to locate the aircrafts. It does this by transmitting radio signals and then receiving the same signal that is being bounced off by the aircraft. The time that elapsed between transmission and reception is being used to calculate the distance between the antenna and the aircraft. The purpose of the secondary antenna is to send interrogation signals and then receive the response signals that are being sent by the aircraft. The device that is in charge of communicating to the secondary antenna is called the transponder. This is the one located on the right. Ground-based radar continuously sends out interrogation signals and receives the responses as it spins around. So, the purpose of the transponders is to receive the signals that are being sent by the secondary radar antenna and then respond by transmitting back radio signals back to the antenna, more or less saying, I'm here. All the information being received by the antennae are being sent and displayed on the ATC's computer radar screen, basically its location and its squawk code. So, what is a squawk code? A squawk code is a 4-octal digits code assigned to an aircraft prior to flight. It contains various necessary info such as route, number of passengers, country of origin, etc. Basically, a squawk code is like the ID of a flight. When a squawk code is not pre-assigned, the default is 1200. And there are three special cases of squawk codes. These are 7500, 7600, and 7700. When 7500 is set, it tells the ground station that the aircraft is being hijacked. When 7600 is set, it tells the ground station that the aircraft has lost all modes of communication. And 7700, it tells that the aircraft is under emergency situation and that the ground station needs to help the aircraft. Using the aircraft-mounted transponder, the pilot enters the pre-assigned squawk code to the transponder, and then, afterwards, it indicates that the aircraft is now ready to transmit its squawk code. In the transponder, there are two modes. The first one is the mode alpha or mode A. Mode alpha indicates that the transponder only transmits the squawk code of the aircraft. Next, we have mode Charlie or mode C. In mode Charlie, the pilot rotates this knob and then the arrow must point to the alt, meaning that the transponder also transmits along the squawk code the altitude of the aircraft. And that's pretty much it. That concludes my report. Thank you for listening. Here are my references.